Good morning, everyone. And thank you very much indeed to the organizers for organizing a very enjoyable and interesting workshop. And for inviting me to give a talk this morning. And thank you very much to the audience as well for making it to the first talk this morning after the dinner and the drinks. When I walked into the bar and I saw 10 shots of some pink substance lying out on the bar, I thought there was 10 casualties for today's talk. Okay, so I'm going to talk about quantum effects specifically on black hole spacetimes. I say inside out because I'll be talking about effects inside and outside black holes. So this is an outline of the talk. The first three-ish sections are quite general. I was asked by the organizers to give some general introduction to QFT and black hole spacetime, so I'll be doing that. So most of you probably will know most of everything I'll present on the first three subsections. The last one is probably known to my fellow Leipzig colleagues, but probably less so to the rest of you. So the four is probably what's going to be newer to you. And I'll finish with some conclusions. So I'll start just by putting the framework in which I'm giving the results. So it's semiclassical gravity, by which I mean that in the absence of a theory of quantum gravity, modulo Renate Lulz and other people's approaches. So what we use is semiclassical theory of quantum gravity. So we leave the gravitational field classical on the right-hand side of Einstein equations. Instead of the classical stress energy tensor, we put in expectation value of the stress energy tensor in some quantum state psi. And that we expect that to give valid results whenever the scales of your physical processes are much larger than Planck scales. Now, that would be ideally within semiclassical gravity. What you would do is solve the full semiclassical Einstein equations. So note here that the stress energy tensor on the right-hand side depends on G, and G is the metric that appears on the left-hand side. So if you have the same metric G appearing on the left-hand side and the right-hand side, and you can solve for that G, you would be solving the Einstein equations, the semiclassical Einstein equations, self-consistently. Now, that's a tall order for most spacetimes. So typically what we do is a perturbative approach. So we fix some classical background, which I denote by G, and say typically it's going to be a vacuum solution of Einstein equations, classical vacuum solution. So G solves those equations. And then you calculate your stress, you place some quantum matter field on the right-hand side of, on that background spacetime, you calculate the stress energy tensor on that background spacetime. And that's what you put on the right-hand side of the semiclassical Einstein equations. And then ideally, you would want to solve for the metric appearing on the right-hand side, on the left-hand side, which is I call G superscript C, meaning the quantum corrected metric. Okay, so this would give you a notion of the quantum effects on your background spacetime G due to the quantum matter fields, which go into the Einstein equation, semiclassical Einstein equations by the expectation value of the stress energy tensor. Even that is a tall order. So that can be done in some particular cases of high symmetry. So just calculating the stress energy tensor is already some interesting results and valuable results because they give you an idea of what the quantum corrected metric would be. So for example, if you've got a divergence in the stress energy tensor, that tells you that there's some serious quantum back reaction effects in whatever region of the spacetime, background spacetime, where the stress energy tensor diverges. Okay, so if that was not enough, challenging enough, on the right-hand side, I say that I put in the stress energy tensor, quantum expectation value of the stress energy tensor, but in fact, it suffers from ultraviolet divergences, as you all know. The stress energy tensor is typically quadratic in the field, which is an operator value distribution. So that gives you, that yields some ultraviolet divergences, and you want to renormalize that. So the renormalized expectation value of the stress energy tensor I'll denote it by the acronym RSET, and I'll be talking about this, giving you results about this later on in the talk. So the RSET is really the important quantity because that's the one that you put in, you really put in on the right-hand side of the semi-classical Einstein equations. Here with G on the left, on the right, if you want to solve them self-consistently, or GC on the left-hand side if you do a perturbative approach. Okay, so that's the framework in which I'm going to be showing the results. And now I'm going to be talking about the background metric G on which we're going to calculate the quantum fields. Okay, before doing that, just one more slide on renormalization. So I don't want to get too technical on renormalization, so I'm not going to give details. But the problem is what's stopping us from making big progress on this approach is the technical difficulties that we have. So I'll give you a flavor of what the difficulties are. So there is typically two approaches for renormalization. One is point splitting, which Elizabeth Winstanley, our dear chair, already talked about. She gave 3 different ways of doing the point splitting. So you temporarily separate the point. Instead of evaluating the RSET at one spacetime point directly, you split your points into 2 points, x and x prime. And you subtract for your separated stress energy tensor some divergent terms, which depend only on the geometry of the background spacetime. They do not depend on the quantum state of the field. This is done in a physically meaningful manner. They obey Wald's axiom, so you want your RSET to be conserved and causal in particular. And then, sorry, whenever you subtract the divergences, you take the limit as x prime goes to x. So you recover your result at your point x where you wish to evaluate the RSET. So that's one approach, point splitting. Another one, which is valuable in some very, very particular places, is subtraction by some reference state. So if you happen to know what the value of the RSET is in some reference state psi over bar, for whatever reason you happen to know that, then you can, the difference between the RSET and the state psi where you want to calculate it and the RSET psi over bar where you happen to know the value of the RSET is just equal to the difference between the unrenormalized expectation values of the stress energy tensor. And that is much easier to calculate from a technical point of view than subtracting those divergences. So I'll get back onto that, to the specific case of Kerr in a few slides, but just a flavor of the technical difficulties and approaches for renormalization in core spacetime. Okay, so now we're in a position to go into the particular background spacetime where I wish to do the calculations. They're black hole spacetimes. I'm just going to talk about Kerr. This is the most astrophysically meaningful black hole spacetime. All astrophysical black holes are expected to be described by the Kerr metric. So this is the Kerr metric in Boyer-Linkwitz coordinates. You've got your delta function, which is, it has two, so you've got your radius r, it has 2 roots at r plus and r minus. R plus is the radius of the event horizon, and r minus is the radius of the Cauchy horizon, about which I'll dedicate the last part of the talk. You've got 2 parameters describing the metric, the mass m and the angular momentum per unit mass a. Each horizon has got an angular velocity, omega plus and omega minus, and a surface gravity, kappa plus and kappa minus. A couple more features about Kerr. You've got a curvature singularity at r equals 0. So r minus, the Cauchy horizon has a radius smaller than the event horizon, and r equals 0 is inside, it's beyond the Cauchy horizon. And that singularity, it's a curvature singularity. It only happens on the equator. It's singularity free off the equator, and has 2 symmetries. The metric does not depend on time, it's stationary, and it does not depend on the azimuthal angular coordinate, so it's axis metric. This is a caricature of Kerr that I did in my PhD. So that's a long time ago, but it's just useful. So after all these times, I still put it on. So you've got your caricature of a Kerr black hole here. And then I just want to point to 2 regions to which I will allude later on. So you've got your killing vector ddt. It's a killing vector because the metric does not depend on t. And dd phi is also killing vector. So any linear combination of those two killing vectors will still give you a killing vector. So in particular, chi given by this, which you can think of as an observer co-rotating with a black hole at the angular velocity of the black hole, omega plus, that's a killing vector as well. So Kerr has got the feature, and technically very annoying feature, that you've got no killing vector, which is time-like everywhere outside the event horizon. In particular, DDT is time-like far away from the black hole, but near the black hole in the so-called Virgo region, it becomes space-like. Contrary obviously to that, chi is actually, it's the null generator of the event horizon, and it's time-like near the event horizon, and it becomes space-like far away. And the region, the hypersurface where it becomes space, it's null, and beyond which it becomes space-like is called is the so-called speed of light surface. Okay, so I'll talk about this. I'll refer to this. These two surfaces have got consequences for the QFT on Kerr spacetime, as I'll show you later on. Okay, so now it's a less caricaturesque representation of Kerr. There's a Penrose diagram. In here, this diamond here, you've got the outer event, the region outside the event, the black hole. You've got Scri plus the future null infinity, Scri minus past null infinity. Past horizon is H minus, future horizon is H plus. You've got the left horizon here, still given by R equals R plus. In the diamond here, you've got your black hole. And these two null hypersurfaces here, that's the Cauchy, the so-called Cauchy horizon. So R equals R minus corresponds to this null hypersurfaces. And here's your singularity, R equals 0. It's only there for theta equals pi over 2 on the equator. And it's a time-like singularity. So on your Penrose diagram, it goes upwards. Okay, so Penrose diagram of Kerr. And this is all for now about your background spacetime on which we're going to be doing QFT. So now I'll introduce the framework in which how we do quantum field theory on black hole spacetimes. I'm going to be concentrating on the case of a massless scalar field phi. In here, it's still classical. And we want to do is solve the wave equation that it obeys. So it's just a standard Klein-Gordon equation. And your metric comes in the covariant derivatives. And it's a homogeneous solution of the wave equation. Now, you can put other fields, quantum matter fields of other spins, electromagnetic fields. You can do linear gravitational perturbations as well, fermion fields, which I'll present some results later on as well. And they all obey, in some manner, they obey a wave-like equation. They obey a second order hyperbolic partial differential equation, which you can solve in a way that I'll describe now. So, and there's a similar wave equation also for the other types of black hole spacetimes, not just Kerr, Schwarzschild, Kerr de Sitter, and so on. Okay, so that would be for finding your classical solution to the wave equation phi, and you still need to quantize the field. So typically what you do is you want to choose a quantum state for the field, and the way to do that is you decompose the field into so-called positive frequency modes, and they are positive frequency with respect to some time coordinate. Okay, and I'll describe the possible time coordinates for Kerr in a second as well. Before doing that, well, actually, here's a case of the time coordinate, which is, you can choose just the Boyer-Linkwitz time coordinate t. So you can actually separate by variables the wave equation in Kerr. The time separation is just due to the stationarity of the spacetime. The phi separation is just due to the axis symmetry of the spacetime. And then there's the so-called hidden symmetry due to a Killing-Yano tensor that allows for the separation between the radial and polar angle coordinates. So this is one way of choosing your modes, which would be positive frequency with respect to your time, Boyer-Linkwitz time t. Now, all the physics, all the meat is in the radial factor psi, It obeys a second order linear ordinary differential equation. So it's a Schrodinger type equation with some potential. Here is a depiction, an actual plot of the potential. As a function of a radius, this is the so-called tortoise coordinate, which goes over the whole real range for when you're outside the black hole spacetime. So there's some scattering coefficients, reflection coefficients, and transmission coefficients. I should say the credit to this plot and other plots goes to my colleague, one of my colleagues, Noah Zilberman, who is in Technion Institute in Israel. Okay, so that's one particular way to do a mode decomposition for your field phi. So this is a description of your general way of doing quantum field theory in a general Kerr spacetime. Most of you probably know this, but just as a reminder, you choose your modes for phi. For example, you want to choose them as positive frequency with respect to the Boyer-Linkwitz coordinate. Then you write your full solution as a mode sum over the modes with some coefficients A, and if it's real valued, you add the complex conjugate to that. You quantize the field by promoting them to operators, the field and the coefficients A, and you have your Hermitian conjugate instead of complex conjugate. You choose your value, your quantum state psi, as the state which is annihilated by the A coefficients. And then you want to calculate the anti-commutator for your field in your favorite, your state of interest psi. You apply a second order differential operator on your anti-commutator, and from that you get your unrenormalized expectation value for the stress energy tensor with your points split x and x prime separate. And then you wish to do your renormalization and get your R set, which you then put on your right-hand side of the Einstein equations, and then you would ideally solve for the quantum back-reacted metric. So quite a few steps, all of which are demanding in some way or other, certainly for Kerr spacetime. Okay, so this is one slide for the procedure and all the steps you would want to follow. By the way, feel free to ask questions or comments at any stage. Yeah. How do I define T or define time? So at the start, I gave the metric in Boyer-Linkwitz coordinates for the Kerr metric. So the time, the Boyer-Linkwitz time coordinate is what I denote by T, but there's different choices of time. So I'll get on to that next or soonish. Yes, yeah, the Kerr metric is stationary. So I'll be talking Kerr metric or tweaks of those, by which I mean Schwarzschild, Kerr de Sitter, Kerr-Neumann de Sitter, and so on, all of which are stationary. Okay, so, right, so another slide on renormalization for the specific case of Kerr. So we already told you about this. You can do it via point splitting. So the way you would typically choose the separation between the points x and x prime is by choosing a separation in one of the symmetries, using the symmetries of your background spacetime. I said that Kerr was stationary and axis metric. So you want to exploit that in order to separate the points x and x prime. This divergent terms, they're, like I mentioned before, they're purely geometric, and they were calculated by Christensen in the 70s. He gave some formal expressions for a general Kerr spacetime. Now, this renormalization, this subtraction, is very, very hard to do technically. The reason is that usually you have mode sums, like the way I've defined the modes, phi I, for the unrenormalized expectation value of the stress energy tensor, whereas for the geometric divergence, as the word says, a geometric, so you write it in terms of the Singh world function, which I think Elizabeth already introduced for us. So they're written analytically in very different types of ways, and you wanted to convert from the language of one geometrical language to the mode sum language, or vice versa. So those two languages, you need a dictionary to go between one and the other, which is not straightforward. just to quote a few people and just to mention in two points the progress made. In the case of spherical symmetry, so for Schwarzschild spacetime, when the angular momentum of the black hole is equal to 0, that's been known to be done since the mid-80s, originally by Anderson, Candelas, and Howard, who really pushed through for all types of spherically symmetric spacetimes. The advantage here is that you can do Wick rotation. You can find your Euclidean green function. Later on by Adrian Otterwell and Elizabeth, and more recently by Peter Taylor and Cormac Breen, and other people have been doing great work on spherical symmetry spacetimes. So that's covered in many regions of parameter space. In the case of Kerr, that's been a lot more challenging. So again, Adrian Otterwell and Elizabeth Winstanley and Gavin Duffy and myself did some calculations indicate that you do differences between quantum state. So no renormalization of that. That still gives you an idea of what happens to in different regions of the space-time and for different quantum states. But these are just differences between quantum states, no actual renormalization. Renormalization in Kerr was not achieved until 20 years later after it had been achieved by Schwarzschild. Just to give you an idea of how hard it's been. So Amos Ori and his colleagues and students, well, Martin van den Ment is not a colleague of him, but he was one of the authors, Adam Levy and Elon in Israel achieved this breakthrough. And these are the only people, and then the results will present later on inside. It's the other case. The only people who have achieved the renormalization in Kerr spacetime. There's no other results to compare against, and this is still a demanding calculation. Coordinate dependence. Yeah. So there is a choice of the time coordinate, if you wish. You define your quantum state based, essentially, that gives you a choice of quantum state. I'll talk about that, I think, probably in the next slides. And then, so you do make a choice of your time coordinate, and so you're making a choice of state, and I'll introduce the two more interesting quantum states. Yeah.
Is there any progress in Is there any progress in the renormalization in coordinates that cover all of Kerr's space-time?
Okay, so if you say space-time, you mean Kerr, and you mean coordinates that cover the whole of it. I presume you're referring to Kruskal coordinates.
Kruskal or know, Eddington.
Yeah. So we'll talk about those, I think, probably in the next slides or very soon. I'll give you a yes-ish.
Okay.
I'll have slides for this, so I'll can give you a more definite answer than that briefly. Okay, so indeed, the next slide is about the choice of the time coordinates, as the audience have been asking for by popular demand. Okay, so as I say, we've got the Boyer linkage time coordinate T and some tortoise radial coordinate R star. They cover, so whenever they go through the whole real range, they cover the outer region of the spacetime. Let me note that v little v, so you can define coordinates u and v in this way: t minus r star, t plus r star. V is a fine parameter along sky minus. You can also define Kruskal coordinates. Okay, so as I say, u and u becomes plus infinity as you approach h plus, and as I say, the full real range of u and v cover only the outer region of the spacetime, so do not cover. You need another patch for u and v to cover the inside of the black hole. Kruskal coordinates, they allow you to go through the h plus. I only define them here outside. You can define them in a similar manner inside. So analytically continued through the h plus. And they're regular on the event horizon. In fact, u is equal to capital U, Kruskal coordinate u is equal to 0 on h plus. And they're affine parameters u is an affine parameter along HL union with h minus. little u, Eddington-Finkelstein u. Little u is not a fine parameter along the pass horizon. Kruskal coordinate u is. Okay, so that's, yeah.
What's the so U and V, are they killing and time-like?
U and V, so U and V are null-ish. So on the event horizon, they would be null.
Okay, so then what is the killing and time-like coordinate?
Well, so they're not killing because they incorporate R, and R is not the metric does depend on R. The killing vectors are DDT. So
DDT, but is it time-like now?
So DDT is time-like everywhere except in the ergo region, in that green region near the event horizon. But it's a killing vector of the spacetime.
Okay. Thanks.
Okay. So that's so I'll be using this. I say time coordinates because you're right. U and V can become null. So when you're near a null hypersurface, they are approximately, they're time-like near, very near a null hypersurface. So I'll still refer to them as time coordinates, even though they can be null. Okay, so now we define modes, specific modes based on specific time coordinates. So in here, I've got, okay, let me start with G in on the right-hand side here. There are pure waves with respect to positive frequency waves, positive frequency modes with respect to little v, with respect to the affine parameter v along scri minus. So that's how you define your ingoing modes. They have zero Cauchy data on H minus, and then you propagate them by Cauchy evolution through into the outside, on the outside spacetime and through into the inside of the black hole as well. The G up modes, they're defined in respect to as positive frequency respect to your Kruskal coordinate capital U on HL and H minus, and they have zero Cauchy data on scri minus. Okay, so I call this the en route modes, G up and G in. They're positive frequency respect to U on the pass horizon and respect to V on scri minus. So they're positive frequency with respect to the fine parameters on the Cauchy hypersurface where you're defining the modes, pass horizon, scri minus. So these are the en route modes. And then you can expand your field with respect to these modes. They form a basis of mode solutions. So here's your up modes and the in modes and the corresponding coefficients. And you define, or en route define the en route state, which is the state which is annihilated by the corresponding in and up coefficients. Okay, so once you've got that, your expansion for the field in terms of those modes, you can calculate the anticommutator, and you readily find it in terms of the modes in and up. Let me say, just give you a yes-ish earlier on for your question. Let me give you a more clear answer, which is the problem about using Kruskal is that the wave equation does not separate in Kruskal coordinates. So what you end up doing is rewriting these modes in terms of Eddington-Finkelstein modes in a manner. You can rewrite your two-point function when the state is in the en route state. Even though you can define it like this in terms of en route modes, you end up defining them in terms of Eddington-Finkelstein modes thermalized in a certain way. Okay, so that's why I said yes-ish. Okay, so what are the properties of the en route state? They have similar properties in Kerr and in Schwarzschild spacetime, which is non-rotating spacetime, black hole spacetime. One feature is that it's irregular on H minus, but regular in the future, in the inside of the future domain of dependence of your Cauchy characteristic initial data surface. It's empty at scri minus, and it contains Hawking radiation at scri plus at a certain temperature, which is proportional to the surface gravity of the event horizon. So essentially, it models a black hole which is evaporating via the emission of quantum thermal Hawking radiation at Scribe plus. This is indeed the way that Unruh, so Hawking came up with Hawking radiation in the 74, and he did it in his own particular geometrical optics way. And Unruh wrote a paper when you define his Unruh state in this manner in the full maximal analytic extension of Kerr spacetime, precisely to model the evaporating black hole that Hawking had uncovered. So these properties were unearthed originally by Christensen and Fulling in the 70s and then Candelas in the 80s. These are just the pioneers, if you wish. More progress was made later on, and in Kerr by Elizabeth Winstanley and Adrian Ottawell in 2000. This was without doing renormalization, but mostly doing state subtraction. But you can do, by doing state subtraction, you can get the properties in the asymptotic regions near the horizons and near infinity. I wanted to include here, I didn't have time yet, but a Christian Klein in Leipzig proved the regularity, I say regularity inside the domain of dependence for the case of Kerr de Sitter. Yeah, okay. So these are the properties of your Unruh state, which really is the most physically meaningful state because it's meant to describe astrophysical black holes evaporating via the emission of Hawking radiation. So here's where your choice of time comes in, because you're choosing, you know, your Kruskal coordinate U and your Anton Finkelstein V, and then you're defining your modes relative to that, and your quantum state relative to that, but it's a physically meaningful and most appropriate, astrophysically appropriate state for the field. Okay, so here's some calculations. Okay, this is another plot from my PhD. So I can't believe I'm doing this, but it gives you a very quick idea. So this is the Hawking flux at infinity. Again, I did not need to do renormalization here. This is at infinity. And for this particular component of the Strasony tensor, no renormalization was required. So you still need to do your mode decomposition, calculate the modes, and so on. And this is the flux at radial infinity as a function of the angle. The pair is axisymmetric, but it still depends on the polar angle theta. So this is your dependence of the flux at infinity as a function of a polar angle theta. This is for the electromagnetic field, by the way. Okay, so these are more proper results. So as I said, there was a significant breakthrough in Kerr. This was due by the Israel Technion group and Martin van der Ment, where they calculated, as I said before, they calculated your set everywhere outside the event horizon of a Kerr black hole. These are the plots for different components of the Stress energy tensor on the equator and on the axis of symmetry for a particular value of A. They got close enough to the horizon, close enough in some sense. I believe they didn't get to the Ergo region, so not extremely close to the event horizon, but still, this is certainly tour de force, a technical tour de force. These are the only results so far in decades of work in black hole, QFT in black hole spacetimes, the only calculation of the R set in Kerr outside the event horizon of Kerr spacetime. Okay, so I introduced the Unruh modes. You can also define the so-called Kruskal modes. So G up is still the same. They're positive frequency with respect to the Kruskal coordinate U on the H minus. And then you can define the capital G capital in modes. They're defined as being positive frequency with respect to the Kruskal coordinate capital V on H plus. So the Kruskal modes now are positive frequency with respect to Kruskal coordinates U and V, which are regular coordinates everywhere in your spacetime, certainly in the inside and outside of the event horizon. So again, you can play the same game. You can expand your field in terms of these modes, the Kruskal modes. Then you can define the corresponding Hartle-Hawking state. So it's the state denoted by H, which is annihilated by the coefficients in the Fourier mode decomposition of the field in terms of these modes. So this was defined by Hartle and Hawking in '76. I'm going to say in Schwarzschild spacetime, some definition of this state was given by Frolov and Thorne in '89. There's problems with this state, which I'm going to talk about in a second, but I mean, they were put forward and they were defined in this papers. You can readily calculate the anti-commutator for the Hartle-Hawking state in terms of the up and capital in modes. What are the properties of the Hartle-Hawking state? I'm going to split the properties into Schwarzschild spacetime and Hartle-Hawking spacetime because they're quite different in the two cases. So in the case of Schwarzschild, they're regular. This is a state which is regular everywhere in your spacetime, including on the horizons and inside the black hole and outside the black hole. It's meant to, or it has properties that model a black hole, which is in thermal equilibrium with the radiation, with the quantum, the thermal Hawking radiation. So it's a state which is relevant for, if you want to do thermodynamics, the black hole of mechanics, and within the ADS CFT correspondence. So some of these properties were discovered by Christensen and Fulling and Candelas in the 70s and 80s. Now, for Kerr, things are a lot trickier. And in fact, it's been proven that no such a state can be defined in Kerr spacetime, for boson fields in Kerr spacetime. So this was proven originally by Kay and Wald. Frolov and Thorne had defined it in 1889, and Elizabeth and Adrian showed what the problems are with the Frolov and Thorne state. So they showed that the Frolov and Thorne state, even though it was put forward, was defined by Frolov and Thorne. Elizabeth and Adrian showed that it's not well defined anywhere outside your event horizon in Kerr. This is for bosons. So people have attempted to define states which are similar to the Hartle-Hawking state. In particular, Candelas, Chernavsky, and Howard in '81 constructed a Hartle-Hawking light state where determinized the modes in a different manner. This is yet another picture from my PhD, and it's the last one, I promise you. But this is a calculation. So this is a difference between two quantum states. Again, I did not do renormalization, as I said. In Kerr, renormalization has only been achieved by the Israel group. There's a difference between two quantum states, but it gives you an idea of the properties of the CCH state, which is the one defined in the 80s by Candelas, Chernavsky, and Howard. And this is the speed of light surface. This is the radius, and this is the polar angle theta. This is the speed of light surface, which I described earlier on, where the null generator of the horizon becomes null. And this brown surface, inside the brown surface, so in here is where the ergo region is. And you can see, and this hat-ish type of surface is the calculation of this particular component in this particular state. And it shows you that it's regular through all the way inside the ergo region and through the ergo region. Okay, so that was for fermions. There's a difference for that was for bosons. There's a difference for fermions, which is one has got certain extra freedom for fermions because you've got modes. There's more modes which have positive norm, and you need your known modes to be positive norm. So there's a lot more freedom to play around with. So indeed, with Elizabeth and Adrian and Sam Dolan and Brian Nolan, we did the calculation of, again, differences between quantum states. And in here, it's the Hartle-Hawking state for fermions and the Unruh state for fermions. And this is a calculation in Kerr outside the event horizon. So, so what's this? So X is theta, and Z. So this is the equator of Kerr. So the yellow is where it's regular, and blue, it's where it's irregular. So the ergo region is inside the red dotted line, and the speed of light surface is where this dashed blue line is. And there's a very good overlap. This is numerical work, so there's a fairly good overlap given the error in the numerics with where the state becomes irregular. So this is telling you that this state becomes is regular inside the speed of light surface. That was not the case for bosons. The Hardwell-Hugging state is irregular everywhere, even inside the speed of light surface. Whereas for fermions, you can define the state which is regular everywhere inside the speed of light surface, and it becomes irregular there. You can think of it as a state which is co-rotating, a thermal bath, which is of fermions, which is co-rotating with your black hole. At the speed of light surface, your velocity, linear velocity of your thermal bath, which would achieve the speed of light, and you cannot define it beyond that. That's a way of physically understanding this.
What does it mean, irregular?
Irregular, I mean that, so we do numerics to calculate this. You do a sum over modes. It's an infinite sum. So in particular, there's L modes. So you do a multipolar decomposition of your field in terms of the spheroidal harmonics, which I didn't mention, but the theta dependence of them. So you do an infinite sum over L modes, and that's some divergence in the blue region. So that's what I mean by irregular, that your Orsted, your renormalized expectation value in the Strezheny tensor in coordinates which are regular in that region becomes divergence. Okay, so that's just one slide on fermions, which is some overview of the results achieved so far. Okay, so now I'm going to dive inside black holes. So let me introduce why the physical context of this. So this is the Penrose diagram of Kerr. And here, instead of having a maximal analytic extension of Kerr, I'm showing you the spacetime you would have if you have gravitational collapse to Kerr. So typically you have, a star, the surface of a star. And so the left side of the spacetime that I introduce later on, typically you would not have that. Part of your right spacetime does survive. In particular, the right part of the Cauchy horizon typically would survive. So that's the Cauchy horizon that is of more physical interest to us. So let's imagine that there is an observer that crosses, drinks the 10 shots that there were in the bar last night, happily and merrily, says, okay, I'm going into the black hole. Bold and full of confidence and drunkenness, crosses the event horizon and then crosses the Cauchy horizon, and then it would run into the time-like singularity inside beyond the Cauchy horizon. The problem there is that you've got a curvature singularity. So the Cauchy initial value problem is not well posed as you cross the Cauchy horizon. In order to have unique Cauchy evolution, you would need to put some boundary conditions on your time-like hypersurface, singular hypersurface. So general relativity ceases to be predictable beyond the Cauchy horizon. On the top of the curvature singularity, we also have closed time-like curves near r equals 0, which also give you physical funny features. Okay, so this led to Roger Penrose to conjecture the strong cosmic censorship. Essentially, what it tells you is that the maximal Cauchy development via Einstein equations of some initial data, generic initial data, generic is an important word here, initial data and some initial surface is inextendable beyond the domain of dependence. So the irregularity in your metric beyond the domain of dependence, the degree of irregularity depends on the specific formulation of strong cosmic censorship. And I'm not going to get into the different ways, but it's been the way of specifically formulating it has changed with time. So the modern version is by Christodoulou. In the case of Kerr, what does it mean? So if your initial data surface is this one here, the domain of dependence of that goes all the way to Scribe plus and all the way to Cauchy horizon. but beyond the Cauchy horizon, you no longer, that's beyond the domain of dependence. So you no longer have unique Cauchy evolution. So as I said, so beyond the Cauchy horizon, the initial value problem or the characteristic initial value problem is not well posed. Thank you. Is not well posed. So what does it happen? What happens if you actually go into the black hole? Does general relativity cease to be deterministic? Well, in practice, in the black holes in nature, you do not have isolated Kerr black holes, but they're being perturbed. Two ways of perturbing them is, well, they're being perturbed by classical or quantum fields, so scalar, Fermion, electromagnetic, gravitational perturbations, and so on. You can have some classical matter and some fields, some emitting some fields, electromagnetic or whatever they are, going through the event horizon, so perturbing your black hole, and some of them can go up all the way to infinity, where we can detect them on Earth. So that would be the case of classical matter and classical field perturbations of black holes. You also can look at the quantum vacuum, which is always there. Even if you don't have other matter sitting outside the black hole, you would always have the quantum vacuum. So the question is, do these quantum or classical perturbations, do they destroy the black hole? Do they destroy the Cauchy horizon of the black hole? Do they become infinite? Do they change the spacetime? Do they back react in the spacetime in such a way that your back reacted spacetime no longer has a Cauchy horizon? So this is obviously a caricaturesque way of describing it. So there's different ways, there's different things that can happen. One is it can create still a singularity, but if this singularity is if it's null or space-like, then if you're a drunken observer that goes across the event horizon, then you're just going to crash into the singularity in a manner similar to what happens if you go into a Schwarzschild black hole. But inside the event horizon, inside the black hole, general relativity would not cease to be deterministic. So that's seen to be a nicer feature than just crashing into the singularity, into a null or space-like singularity. Just a comment, which is a similar Cauchy horizon exists for electrically charged black holes in the case that you have a cosmological constant, whether it's positive in the case of de Sitter or negative in the case of anti-de Sitter. Cosmic censorship is a hypothesis, so we need to verify it. And there's questions of if the Cauchy horizon becomes irregular, if you have a hypersurface that becomes inside the event horizon that becomes irregular, is it null? Is it space-like? How irregular is it, and so on. So there's many interesting questions to address. Okay, so the clays, just a comment on the classical irregularity of the Cauchy horizon. In the case of Kerr, that's been shown to hold in the sense that the field is C1 is continuously differentiable, but it's not C0, sorry, it's C0, so it's continuous, but not differentiable. So so this is purely classical results. So it's meant to be a so-called weak null singularity. So it's not C1. So the second order derivatives of the metric with respect to coordinates, critical coordinates, which are regular in the event horizon, they diverge as v goes to infinity. So as you approach, so they diverge as in this manner. So there's exponential modulo some power of v. Okay, the power of v depends on the specific field that you're looking at. So these are results by Ori and de Fermat. Ori within theoretical physics and de Fermat and Luc within mathematical physics. Okay, now still within classical, there's a couple of slides on classical perturbations. So in the case of Kerr ds, Kerr de Sitter, so the Cauchy horizon is shown to be irregular under classical perturbations. So strong cosmic censorship is preserved. In the case of Rational Nostrum de Sitter, so whenever you have charge, electrical charge, that is not the case. So Rational Nostrum de Sitter, so these are spherical symmetric charged black holes asymptotically de Sitter. The Cauchy horizon remains regular. So strong cosmic censorship is violated classically for these black holes. So this was shown by Cardozo and collaborators. In the case that you also include rotation, Kerr-Neumann de Sitter, this is work I did with a student of mine, Cassia Marino. So this shows you the perturbations of the Cauchy horizon up above this line. The Cauchy horizon is stable, so you would have violation of strong cosmic censorship for Kerr-Neumann de Sitter black holes classically. So this is for different fields, spin 0, spin 1/2, and different values of the angular momentum. So above this line, this would give you violation of strong cosmic censorship in Kerr-Neumann de Sitter classically. What happens when you include quantum effects? Thank you. What happens whenever you include quantum effects? Conscious about my time. Okay, one slide, I think, on the case of three dimensions. So I alluded to these results in the discussion panel yesterday. So in the case of 3 dimensions, because it's just easier to do analytical calculations. So together with collaborators, Alessandro Fabri, who is now in Valencia, Martin Martinez. I'm getting confused with Edu. Martinez and Zanelli in Chile. We did a calculation, analytical calculation of the quantum back-reacted metric. So in this case, it's one of the few cases to my knowledge where you could calculate you could solve the semi-classical Einstein equations for the quantum back-reacted metric. So we calculate analytically the stress energy tensor that you put on the right-hand side, and then solve analytically for the case of rotating black holes in 2+1 dimensions in their anti-de Sitter black holes, asymptotically anti-de Sitter black holes. We could calculate analytically the quantum back-reacted metric. So we really have a very good analytical hold on the properties of the quantum back-reacted metric. And indeed, for some regions of parameter space of the cosmological constant and so on, there is a divergence in the R set and the scalar curvature. You can see how strong this divergence is, and it is strong enough that for some other subregions of parameter space, the singularity becomes space-like. Okay, so this is in 2+1 dimensions where we could do a lot of analytical progress. What about in the case of 3+1 dimensions? This is in the case of spherical symmetry. So in the case of spherical symmetry, the stress energy tensor, the VV, in Kruskal coordinates, VV Kruskal, as V goes to infinity, as you approach the Cauchy horizon, it goes like this. So it diverges at the Cauchy horizon. In the case that, so this is for spherical symmetry, in the case that is Rising nostrum, so asymptotically flat charged, asymptotically flat, this was shown again by the Israel group, Amos Ori and his students, Noah Silverman and Adam Levy. In the case of Rising nostrum de Sitter, Stefan Hollens and Jochen Zahn in Leipzig and Bob Wald in Chicago showed just recently in 2020 that there's this divergence of the R set on the Cauchy horizon. Remember that in the case of Rising nostrum de Sitter, under classical perturbations, the Cauchy horizon remained regular. There was a violation of strong cosmic censorship. So what these guys showed, if I can call Bob Wald and Stefan Hollens and Jochen Zahn guys, is that there is violation. Is this going to be? Okay, so what these respectable researchers showed is that there's a divergence on the Cauchy horizon, and so there is your cosmic censorship is restored, and it is you can think of quantum physics as acting as a cosmic censor. Okay, what about Kerr? So in the case of Kerr, there's indications that the R set would diverge. So again, Elizabeth and Adrian showed this, and Hiscock and Yates. There are only indications that they showed that probably under if some condition is satisfied, which they could not prove, but it's likely that it is satisfied without being able to prove it. But if that condition is satisfied, then either part of the Cauchy horizon would diverge. So these are indications that would diverge, but no proof as such. Okay, so we did the calculation with Adrian Ottawell and Amos Ori and Noah Zilberman in Technion in Israel. We did the calculation of DR set inside the event horizon of a Kerr black hole. Just to tell you what the physical features are going to be, if VV in Eddington-Finkelstein coordinates is non-zero, then there's a divergence of the DR set on the Cauchy horizon. So this is why VV is important. It also tells you the contraction and expansion of an observer as it approaches the Cauchy horizon. So the tidal deformation of a drunken observer trying to cross the Cauchy horizon. In the case, I think there is a, oh no, sorry, that's fine. So this is for the VV Eddington-Finkelstein VV components. For the UU components, it tells you whether what's the deformation of the Cauchy horizon, whether it's going to contract or whether it's going to expand. So that depends on the sign of the UU components and the VV components. So the sign have got interesting physical features and then on vanishing as well. So as I said, with my collaborators, we calculate the fluxes and phi squared inside the event horizon of Kerr. These are, well, in fact, it's not even published yet. For phi squared, this work where there's a draft, but they allowed me to put it in. So this is value of phi squared inside the event horizon. This is a function of the radius. Let me go to the fluxes, which are the most interesting results. So these are the fluxes inside the event horizon. This is the UU component and the VV component. So this is the Cauchy horizon here, and this is the event horizon here in the case of when you are on the axis of symmetry. Remember, this depends on the polar angle theta. So two things to point here. At the Cauchy horizon, they are non-zero, so that would give you a divergence of the R set in Kruskal coordinates on the Cauchy horizon, and also the sign changes. Well, sorry, this what we're interested in is the sign on the Cauchy horizon. Here, in this case, it's positive for the axis symmetry. Sorry, for the axis of symmetry, and there is some oscillations as you approach it. This is as a function. Okay, so this is still on the axis of symmetry. This is for, in the case, as a function of A, as a function of the angular momentum of the black hole. So there's some interesting features as you approach extremality. So as A goes to M, there's some oscillations, and it goes to zero as you approach extremality. The thing, as I said, TVV is non-zero in Eddington-Finkelstein coordinates. That tells you that in Kruskal coordinates, TVV divergence. And in fact, it diverges in a way that is stronger than the classical divergence. Remember, I introduced what the classical divergence is in the case of Kerr, and it was divergence exponentially in Eddington-Finkelstein V, modulated by a power law in V. That's not the case of quantum corrections. So the quantum corrections really give you the stronger singularity on the Cauchy horizon. So it's a dominant divergence for astrophysical black holes. This is near extremality so this is log epsilon, which is epsilon goes to zero. You approach extremality, so log epsilon goes to minus infinity. In here, you're approaching extremality, and you can see clearly the oscillations as you approach it. This is a function of theta. So far was on the axis of symmetry. There's a theta dependence, and indeed the signs of TUU and TVV vary with theta. So whether there's going to be contraction or extension of the Cauchy an observer crossing the Cauchy horizon or the Cauchy horizon itself, that will depend on the value of theta. So what the quantum back-reacted metric would be in this case is actually very tricky, because the sign of the fluxes will depend on the value of theta. So which one is the interesting value of theta? Will it happen differently for different values of theta? Will it contract or deform depending on the value of theta? Do you need to value average over theta? All these are open questions for the quantum back-reacted metric. So as I say, this is just in writing what I say. And tentatively, what our results are showing is that for some cases, it might actually yield a null singularity, as opposed to a classical singularity in the space-like case. But all this is still up for investigation, future investigation. This is just to check on our results as you approach the horizon. We did in 2 different methods, just to gain some confidence on our numerical results. We did in 2 different ways, time splitting and also stage subtraction, and there was agreement between those. This is just, if you don't trust our results, this is a check on them. Okay, so to conclude, the quantum effects on the Cauchy horizon of black hole spacetimes are typically stronger than the classical perturbation effects. In the case of asymptotically de Sitter, they're strong enough to actually restore strong cosmic censorship, at least in the case of a spherical symmetry. In the case of the rotating case of Kerr, Neumann, de Sitter, that still needs to be shown. And in the case of Kerr, the divergence in the Cauchy horizon due to quantum vacuum fluctuations is stronger than the case of classical perturbations. And the signs of the fluxes depend on the angle theta and on the angular momentum of the black hole as well. In the case of 2 + 1 dimensions, we managed to calculate analytically the quantum back-reacted metric and what happens to the quantum back-reacted space-time in the case of Kerr. That's still up for investigation. So thank you very much for your attention.
Thank you very much indeed, Marc. Now you have a strategic decision to make as to whether you want to ask questions now or with a cup of coffee in your hands.
Yeah, thanks for the very interesting talk. What determines the exponent n in the divergence of the classical piece, I guess?
It depends on I know it depends on the spin of the field, and I know that that divergence is state independent. I can't remember how it depends on the value of this field. Maybe Christian or other people know about this. These were not results of mine. I know it depends on the spin of the field.
But are they integers?
I would say so, tentatively. Or half integer, not more than half integer.
Okay.
I think it's integer. Yeah.